Hello and welcome to this tutorial. In this lesson, we're going to be looking at 4 different thermodynamic processes. In addition to looking at and introducing and applying these thermodynamic processes, we're also going to be looking at how they are viewed and illustrated on a pressure versus volume or PV diagram. So let's begin. Please remember to pause or rewind the lesson as you need to. When keeping track of thermodynamic processes and cycles that occur in a sample of gas, it is useful to use graphs of pressure versus volume. These are called PV diagrams. Okay, we're going to be illustrating how we can not only use PV diagrams, we're going to illustrate how we can use the ideal gas law, PV equals nRT, or we can use a case of proportional reasoning, which states that the change in pressure and the change in volume is proportional to the change in temperature. So we can kind of use that as well. Ideal gas law will be very useful if we want to find the pressure, volume, or temperature at one particular state, meaning the pressure, volume, and temperature has not changed. However, this or combined gas law become very useful when the pressure, volume, and temperature do change. Okay? But I want to specifically focus on the proportional reasoning version of ideal gas law, as it is really efficient and really easy to use when practiced. So let's go ahead and begin. Basic processes. Part 1. Consider a closed container of gas. Well, right away, closed container means that the volume cannot change. Okay, it's a fixed volume, and you can see a picture of it over here on the side. It encloses a certain volume at V naught, a certain pressure at P naught, and a certain temperature at T naught. Okay, part A, plot the graph to the right. So we're going to go ahead and go on the graph, and we're going to plot a point right here, P naught and V naught. And next to that point, we're going to plot its corresponding temperature, which would be T naught. Part B, if the gas were heated, what would happen to the volume and pressure? Describe what would happen and show the result on the plot. Well, the volume will not change. Right? Remember, it's a closed container. Closed container means it's a fixed volume. Okay. The pressure, on the other hand, so heating the gas will make the molecules move faster. This increases the energy and temperature of the gas. Okay, so what that basically means is this means more collisions. The collision rate goes up. So more collisions, more pressure. Pressure goes up. What became of the heat that was added? Well, the added heat increased the internal energy of gas. And by the way, when you see the word system, that always applies to gas. Part D, what happened to the temperature of the gas? Well, the temperature of the gas is going to increase. Now, how much is it going to increase? Well, it says suppose the pressure went to 2 P naught. Remember, the volume didn't change. So, and this is where we can kind of use proportional reasoning here. Temperature is proportional to the change in volume times pressure. So the temperature, the pressure doubles at a constant volume. Remember, if something doubles, we're going to replace the variable with the number 2. We're replacing volume with the number 1 because 1 represents no change. And we get 2. So what that basically means is 2 times the original temperature. So the temperature is basically doubled. The temperature has doubled from T naught to 2 T naught. All right, and then what we'll do is we'll go ahead and label this. So the way we would label this is draw an arrow to show the increase in pressure, okay, to 2 T naught of temperature. Part 2, consider a closed container of gas. So this time it's still a closed container, but this time it's sitting on an ice bucket. So what that's going to do is that's going to help remove the heat. So the gas is now cooled this time because the heat is removed. So what's going to happen to the volume and pressure? Well, what's going to happen to the volume is nothing. Volume does not change. The pressure, on the other hand, is going to decrease. Right? Because the collision rate goes down. Right? Why does the collision rate go down? Well, as you cool the gas, what are you doing? The molecules themselves are going to lose internal energy. The internal energy of the gas, plus the kinetic energy of the gas, go down, right? The collision rate goes down, the pressure will be less. So what decreases in equal measure with the heat removed? Well, the internal energy decreases. What happens to the temperature of the gas? Well, specifically, it says, what was the temperature of 2V of gas when the pressure was 2 P naught, and what did it become if the pressure went down to P naught? Okay, write the temperatures in terms of T naught and at the corresponding points on the plot. Well, basically, what ends up happening? We're starting at these conditions. We're starting at a value of a volume of gas of 2 V naught and a pressure of 2 P naught. Okay. Now, if we use proportional reasoning with that, then what that tells us, the initial, if pressure times volume is proportional to temperature, that means 2 P naught times 2 V naught, right, corresponds to 4 T naught, right? 2 times 2. Or 4 times, I guess, what would have been the original temperature from the previous example. So we can go ahead and plot that over on the graph here. Okay, so 2 P naught, 2 V naught corresponds to 4 P naught, P naught, V naught, which is 4 P naught. Okay. And what's going to happen with that gas? Well, it's basically the pressure is reducing from 2 P naught to P naught, like this. Okay. So now if you're cutting the pressure in half with a constant volume, that means the temperature cuts in half as well. Because process one and two occurred at a constant volume, they are called isochoric or isovolumetric. Notice that no work is done in this kind of process. The first law of thermodynamics simplifies to the following. Well, the first law of thermodynamics can be written as the change in internal energy is equal to the heat added plus the work done on the gas. But there is no work done on the gas because remember, work is equal to pressure times a change in volume. If there is no change in volume, okay, constant volume means there's no change in volume, then there's going to be no work. So this is how the first law will simplify. Part G, write an expression for the heat in terms of the number of moles, the molar specific heat, and of the gas at a constant volume CV, and the change in temperature. So we can write that as Q is equal to NC delta T, where N is the number of moles, Q is the heat, C is the molar specific heat, and delta T is the change in temperature. Now, the only thing I'm going to add to this is I'm going to add CV because this occurs at a constant. Okay, part 3. Consider a cylinder of gas with friction walls and a weighted piston enclose a certain volume of gas V naught and a certain pressure of 2 P naught under a certain temperature of 2 V naught. So let's plot that. V naught, 2 P naught. That would be right here. Now, if temperature is proportional to pressure and volume, that means this would be 2 T naught to begin with. The piston is free to move up or down. Well, what holds the piston up? Pressure from the gas, which basically is the gas particles colliding upward on the piston. Okay, so we plotted the point already. Part C, if the gas were heated, what would happen to its volume and pressure? Well, here's the thing about pressure. Well, you can see you have the pressure from the gas pushing up on suspending the piston, but then from above you have pressure pressing down due to the weight of this block here. Now, since the weight of the block doesn't change, the pressure will not change. So pressure stays constant, okay? But what's going to happen is the volume is going to increase, sorry, if we're adding heat to it. Okay, so now how do I plot this? Okay, well, it says what happens to the temperature of the gas? Suppose the volume goes to 2 V naught. So that would be this point right here. Which now at that particular location, 2 P naught times 2 V naught would give you 4 T naught. Or another way you could think about it is you doubled the volume at constant pressure. That means you doubled the temperature from 2 T naught to 4 T naught. So the temperature doubles from 2 T naught to 4 T naught. Part 4, consider another cylinder, of gas with a frictionless piston. It encloses a certain volume of gas at 2 V naught and a certain pressure at P naught. So that would be right here. The corresponding temperature would be 2 T naught. Part B, if the gas were cooled, what would happen to the volume and pressure? Well, again, same scenario as last time. The pressure remains constant because it's balancing the weight, and the weight of the block applied on the area, right, is producing pressure. So the pressure from above balances the pressure from below, and that stays the same. So, but this time the pressure, right, still stays constant. But this time the volume is going to decrease. Okay, so now what happens to the temperature of the gas? Well, the temperature of the gas was, what was the temperature at 2 V naught? Well, we figured that out already. And now the volume goes down to V naught. Okay, so in other words, oh, did I do the other? Oh, I forgot. There we go. Okay, so now I'm reducing the volume in half with constant pressure. So since the pressure remains constant and the volume cut in half, that means the temperature has to cut in half. Well, half of 2 T naught would be T naught. Okay, and so that's what we can say about what happens to the temperature in part C. The temperature decreases from 2 T naught to T naught. Part 5, because processes 3 and 4 occur at a constant pressure, okay, they are called isobaric. So isobaric means constant pressure. Write an expression for the heat in terms of the number of moles, molar specific heat at constant pressure, and the change in temperature. Well, it's still the same equation that we saw last time. Q equals N times C times delta T. In other words, the heat is proportional to the amount of gas and the change in temperature, right? But here's how we can kind of change it. This one is going to be NCT for constant pressure. Part 6. Work is done in this kind of process. Determine the expression for work as follows. Okay, well, write an expression in terms of force, and pressure is equal to force divided by area. Write an expression for the change in volume in terms of the distance the piston moved D in cross-sectional area A. Well, volume, okay, or the change in volume really, is going to be equal to, right, area times distance. Okay, now multiply the expression for pressure by the expression for change in volume. So for pressure, remember, was force times area, and change in volume was area times distance. So if we multiply this times this, okay, we get force over area times area times distance. And you can see the areas cancel. What are we left with, guys? We're left with force times distance, which is the work. Okay, so that's how we can basically get work, is pressure times the change in volume. Part D, distinguish between when positive work done on a gas, negative work done on a gas, and when no work is done on a gas. Well, okay, so positive work is done on a gas when the piston falls. What does that mean? The volume decreases. When the volume decreases, the gas molecules move faster. If the energy goes up, positive work was done with that. Negative work is just the opposite. Negative work is done on a gas when the piston rises, meaning the volume increases, right? When the volume increases, when the volume increases, the energy of the molecules, the molecules start to slow down. So the kinetic energy and internal energy slow down. So when the energy decreases, negative work, right, has been done. Okay, and no work is done when the volume stays constant. So the volume has to change in order for work to be done. Okay, so we're going to calculate the amount of work done on this thing. So in process one. So for process one, go back to question one, all the way to question one. Okay, how much work is done in this process here? Well, you can see there's no change in volume. So since there's no change in volume, the work for process one is equal to 0. Okay, now how about question two? For question two, we'll see. Same concept, also no change in volume. So for question two, there is no work done. Okay, questions 3 and 4 both had a change in volume. So in 3, we had expanding gas. Work done on an expanding gas is negative. Think about that. Expanding gas, bigger volume, molecules slow down, right? Energy decreases. That's negative work. So work on an expanding gas is negative, okay? And we're gonna find the value of that work in just a minute. So I'm just writing it down conceptually. And then part 4, question 4, we had a compressed gas. Work done on a compressed gas is positive. And again, we can think about that, but a compressed gas, we're making the volume smaller, right? The energy goes up, right? And so an increase in energy corresponds to positive work being done. Now, let's calculate the amount of work that was done. So for part 3, work is equal to pressure times the change in volume. Okay, well, what was that? The pressure was 2 P naught, and the volume changed from V naught to 2 V naught. Okay, so the pressure was P naught, and the volume changed from 2 V naught, from V naught to 2 V naught, the difference which is V naught. So we get negative P naught V naught, because again, the work done on this process is negative because we're talking about an expanding gas, right? Work done on an expanding gas. Oh, I'm sorry. 2 P naught, negative 2 P naught. All right, and then in part 4, right, we're finding the work again using pressure times the change in volume. Similar idea. This time the pressure, though, is at P naught, stays constant, and the volume changes from V naught to 2 V naught again. Okay, so the difference in that one is going to be a positive P naught V naught, or positive pressure times the change in volume. Positive pressure. positive work done on a compressed gas. Okay, part 7, okay, advanced processes. It is possible to heat the gas in our cylinder piston arrangement in such a way to let it expand and undergo a drop in pressure such that it doesn't undergo a change in temperature. So in other words, what that means is the pressure rises as the volume drops at the same rate, or vice versa. The pressure might drop as the volume rises at the same rate. And if they rise and drop at the same rate, the temperature, that is the proportion of the product, is not going to change. Consider a sample of gas that starts at V naught and 2 P naught. Okay, so we're going to start right here. The corresponding temperature would be 2 T naught. Okay, now it's going to expand in such a way that the volume expands to 2 V naught and the pressure drops to P naught. The corresponding temperature here is still 2 T naught. Okay, what was the temperature in beginning of this process, right? The temperature at the beginning of this process right, was 2 T naught in both cases. Now, does the internal energy increase, decrease, or remain constant? Well, it's going to remain constant, and here's basically why. If the temperature stays constant, then the average kinetic energy, and thus the internal energy, stays constant. Now, how can the first law be written to simplify this process? Well, it can be written as delta U equals Q plus the work done on a gas, but delta U is 0. So delta U remains constant. To say that delta U remains constant means the change in internal energy is there isn't it. Okay? So what that means is this is how it gets rewritten, or you could say that Q, right, is equal to the negative of the work done on the gas, or Q is equal to the positive of the work done by the gas. Remember, something to note, work done on the gas is the negative of work done by the gas, and vice versa. They're opposite perspectives. On the gas is when we compress it, by the gas is when the gas is pushing to expand. So they're opposite perspectives, therefore they're going to have opposite signs of work. Because the temperature remains constant, this process is called isothermal. Lines of constant temperature on PV diagrams are called isotherms. Sketch out a few to the right. So basically, it would kind of look like this. Isothermal curves would be ones that sort of decrease at the same rate. You can see pressure is dropping at the same rate that volume is increasing. It would kind of look. Those would be examples of isotherms. If the gas had undergone the reverse process, contracting under in increasing pressure. So basically what that means is it could have gone in either direction, isothermal expansion or compression. Part 8. It is possible for our cylinder piston arrangement to cool in such a way as to let it expand and undergo a drop in pressure while no heat is added or removed. Consider a gas that starts at 2 P naught to V naught. Okay, so right here, and you can see that its corresponding temperature would be 4 T naught. It cools in a way that it expands to 3 V naught and at a pressure of P naught, which is right down here. Now, that's going to cool to a temperature of 3 times 1 or 3 T naught. So you can see the temperature drop. So the temperature at the beginning was 4 T naught. The temperature at the end was 3 T naught. The first law of thermodynamics could be rewritten. Delta U equals Q plus the work done on a gas. Well, there is no heat, therefore the change in internal energy is completely based upon the work that's done. A process in which heat is neither added nor removed is called adiabatic. Lines along gas that move on a PV diagram when no heat is added or removed are just simply referred to as adiabats. Okay, sketch a few of these lines. Well, the difference between isothermal and adiabatic on a PV diagram is going to really the steepness of the curve. So adiabatic processes are going to be drawn very steep like this. And again, they can go in reverse order. You can have adiabatic compression or expansion. The processes described in the springboard are building blocks of thermodynamic cycles. These cycles are the basis for heat engines, such as what are used in internal combustion engines, such as the kind that are still used in automobiles. Whenever heat is used to do mechanical work, thermodynamic cycles are involved. We're going to learn about thermodynamic cycles next time. I hope you found this tutorial to be helpful. See you next time.